Welcome back, pre-calculus students. We're going to take a look at a couple of different names of systems and types of systems and how to handle them and what they mean. The first one is a system that has at least one solution. It can have more than one solution, but at least one solution is called consistent. For us, linear solutions would be consistent if they have one solution. We're going to take a look at what they mean when we have two lines that have an infinite number of solutions. And eventually, we're going to get into the possibility of having multiple solutions when we're not dealing with linear systems of equations. But in a system with exactly one solution is what we call independent. It's called independent because the two lines don't rely on one another to generate the solutions. There's only one answer. There's only one time when those two places intersect. That's the only point that makes both those lines through. Next, a system which intersects at all points, therefore having an infinite number of solutions, they make the same line. The fancy name we give to the same lines are coincidental lines, which makes it what we call a dependent system. The way this works is if you have something like, I don't know, y equals 4 plus x and 2y equals 8 plus 2x, when we reduce those down, these are the same line. The line would look something like this. Reduce down the other line, it looks something like that. The reason why we say that they're dependent is because a lot of times we just, the answer depends on what our x value is. I'll show you how to handle that in our solutions when we come across coincidental lines or dependent systems in one of our examples. A system with no solution is called inconsistent. For what we're facing in this section, in this chapter, inconsistent solutions means that there's no place of intersections. A lot of times you'll end up getting inconsistent solutions means you'll end up with something like 0 equals 7 or some number. Some number 1 will equal some other number 2. Something that's impossible. Because you know that's impossible, you know that there's no solution. So let's take a look at how to solve a system using, we're going to use elimination to solve this solution. It kind of looks a little bit different. The order at which things kind of are exists a little bit, a little out of place. What we're going to do is mess some things around to come up with the same position. I'm going to take 5y minus 15x equals negative 20, and I'm going to take my y to the other side, so 3y minus 9x equals negative 12. Now, rather than multiplying, I'm going to be a little bit observant and say that there's a factor of 5 buried in that first equation. So this system is the same thing as y minus 3x equals negative 4. Similarly, there's a factor of 3 in my second equation, so y minus 3x equals negative 12, negative 4, and oh my gosh, these are the same lines. If you were to solve this using elimination, you could reach the same conclusion. I could multiply this one by 5, and this one by 3, this one by 5, and we end up with 15y minus 45x. 45x equals negative 60, and 15y minus 45x equals negative 60. Again, same solution. When we add these, we get 0 equals 0. We add, we get 0 equals 0. These are two different ways to solve the same equation, but in either way, we're getting a statement that says 0 is equal to 0. Well, when does that happen? It always happens. 0 always equals 0, which makes these dependent. That makes this a dependent system. So the way we give our results is in terms of generalities. We're going to make a point. We're going to take this line, y minus 3x equals negative 4, and we're going to say we've got a point P, comma, and in goes a P. Y minus 3p equals negative 4. We're going to solve for y. Y equals negative 4 plus 3p. So p comma negative 4 plus 3p becomes our solution.